Hey, welcome back. In this lecture, we will be discussing graph traversal algorithms, the sort of graph equivalent of pre-order and post-order and such. We would have generally done these algorithms even before Dijkstra's, because Dijkstra's perhaps would have tied into this a little bit if you had seen this first, in terms of something I'm going to mention a little bit later on. But I wanted to make sure we went over some of the harder algorithms first so that you could kind of see them in section. These next few algorithms on the graph traversals and even topological sort, the next lecture, are relatively straightforward, and therefore I think that I prefer to get the minimum spanning tree and shortest path algorithms out of the way so that you could also review them in section, and you had more exposure to the harder stuff and the easier stuff. If you just see it in lecture, that shouldn't be a big problem. So now we've gone over some of the harder algorithms, we're going to go back and at least touch on the basic traversals, one of which like I said, we've dealt with a little bit to some extent without really realizing it, and one of which, of course, we haven't seen at all yet. So I'm going to start out with an unweighted graph. We could, of course, do these on weighted graphs as well, but I'm not really going to be too concerned about the weighted versus unweighted. The only issue that would be a problem if we had a weighted, the only issue that would affect our traversal would be whether it's directed or undirected, because in that case then certain edges you don't have the ability to follow in a certain direction, and certain edges you would. But whether there's a weight on the edge or not doesn't have anything to do with whether you can follow that edge from one vertex to the next, and so the weights on the edges aren't really an issue, and I'm just going to leave them off so as not to clutter the picture. So here we have a graph. I'm going to make this an unweighted graph, but certainly undirected graph, but certainly if it was directed, you could only proceed in the direction of the actual edges rather than proceeding in the direction of, here we essentially have an edge in either direction. If I had an arrow on one of these edges, then I can only proceed in the direction of the arrow, from the source to the target. And the first traversal method, or actually in general for traversal methods, we want to basically visit the vertices one by one like we did for trees. Or for lists, actually. But a list traversal was just going from beginning to end of the list, and arrays the same way. For linear structures, it was easy. For trees, we had 4 different algorithms we looked at: level order, and pre-order, and post-order, and in order. And they involve different ways in which we look at the children of a node as compared to the node itself. And for the concept of the graph algorithms, they're not much different than the tree algorithms in the sense that with a tree, every node had particular neighbors, or particular children, and with a graph, every node has particular neighbors. So from A, we have neighbors C, D, and B, and from H, we have neighbors G, E, and F. And so, we can still say I have a bunch of nodes I can move to from any particular node I might be at. And the only issue at that point is if we do such a thing, then there's the issue of not backtracking. I don't want to say, or not getting caught in the cycle. I don't want to say go from A to vertex D, and then from E to vertex C, and then from C to A, and from A to D, and from D to C. We can get kind of wrapped up in this cycle where I keep saying, well, every vertex is the neighbor of some other vertex, and so from A I go to its neighbor D, and from D I go to its neighbor C, and from C I go to its neighbor A, and we just sort of gets caught in this cycle. So as a result, that couldn't happen with trees, of course, because you couldn't have, we were only traversing down the child pointers, not the parent pointers, and with a tree, you couldn't have the child of some node be its ancestor. That, of course, doesn't make sense in real life. You can't be your grandparent's parent, and unless you're reading some goofy science fiction novel. And likewise, you couldn't have that with trees. And with graphs you can. D is A's neighbor, and C is D's neighbor, and A is C's neighbor. And so you can have these cycles, and therefore, what we'll need to do is mark the vertices as we reach them. The issue being that as we reach these vertices, we want to signal that, okay, I've reached a particular vertex. If you reach it some other way, don't continue to process it, because you've already reached it and you're processing it once. And so that will be what is necessary to deal with. in that respect. You sometimes, as we reach them, could be as we process them, depending on exactly how we approach things. We saw, for example, with Dijkstra's, though we could reach a vertex a number of times, we didn't mark it known until we were ready to build calculations off that vertex. So some of the algorithms that get based on these traversals, you'd have that kind of idea instead. But essentially what we're trying to do is make sure you don't use the same vertex multiple times. And so that's going to be the idea here. So the first traversal method we will look at is known as breadth first search. And what this is going to proceed to do is to search broadly first. And of course, the question is, what on earth does that mean? Well, this is going to be very similar to level order traversal on a tree, where I have here the tree. Here's B, and here's E, and there's B, F. No, that's A. There's H, and let's say we start at A. From A, I have neighbors C, D, and B. So let's go ahead and list those as sort of children of A here. I can say, well, from A I could reach C, and from A I can reach D, and from A I can reach B. And the idea now is that now that I've looked at all the neighbors of A, that's sort of the idea of searching broadly. We don't just look at one neighbor of A or a couple neighbors of A. We sort of look over the entire kind of broad spectrum of all the neighbors of A at once. Of course, we can only process one at a time, but we look at all the neighbors of A before we move on. Now that we've done that, we now search over those vertices one by one and look at their neighbors. And so I can say, well, what are the neighbors of C? And I say, well, G is a neighbor of C. A is a neighbor, but that's already in this traversal tree, so forget about that. And likewise, D is a neighbor, but that's already in the traversal tree. We've already added that. We would have marked it. We'll put up the algorithm in a moment. Likewise, we say from D, what are the reachable neighbors? And we have G, which of course we've already put in the tree. And we have C and A, which are already in the tree. And we have E, which is new. And from B, what can we reach? Well, we can reach A, which is already there, E, which is already there, and F. And now we say, well, what can we reach from that collection of items? And from G, we can reach H, and also E, D, and C, which are already there. And likewise, from E, everything we can reach from E is already there. Everything we can reach from F is already there. And everything we can reach from H is already there. And so that's sort of our traversal path for the breadth first search. And if you'll notice, this is basically a shortest path, gives you a shortest path algorithm on an unweighted graph. You sort of say, well, if this is your source, first you're looking at all the vertices you can reach in length 1, or one edge from the source. And then from there you look at all the vertices you can reach in 2 edges from the source. And from there you look at all the vertices you can reach in 3 edges from the source. And then from there 4 and 5 and so on. That's essentially what we're doing. So this is very much like level order in that we're proceeding level by level. You have some starting point, and then everything 1 edge from the starting point, and then everything 2 edges from the starting point, and everything 3 edges from the starting point. And we don't really care which path is taken. So for example, I could have gotten to D by going to A to C to D, G, or A to D to G. Either way is okay. So if D had happened to be the first neighbor, I would have looked at E and G from D, and I would have had a tree like this. If I had had D as my first neighbor, and then C, and then B, well, from D I would have looked at G and E, and then from C I would have had nothing to look at except for, that would be it. And from B I would have had only F to look at, and then I would have had H here. So depending on the order in which we can approach the neighbors, we can get different breadth first trees. And this is known as a, I'm going to write it over here, breadth first span spanning tree because it spans the graph just like the minimum spanning trees we talked about, and it's based on a breadth first search. So what we're building here is a tree that sort of indicates how we did our breadth first search. Where we have here, this looks too much like a little b, so let me make sure that looks like it. We have here the children we've looked at, and then their neighbors, their neighbors, their neighbors, and so on. And of course, you know, if I had looked at B first and then D and then C, we would have gotten a slightly different rearrangement, but it still would have been a breadth first arrangement. It's just a matter of all breadth first means is you look at all the neighbors of all your vertices one at a time. And so we say, or you're saying, look at all the neighbors of the source, and then the order in which you looked at those, you look at their neighbors. And the order in which you looked at those, you look at their neighbors. And so the code for this, which we'll write out in a second, is going to be very, very much like level order traversal for a tree. All we'll have to add is that marking concept we talked about earlier, where we mark vertices as we reach them, and so then we make sure we're not further processing a vertex that's already marked, where we didn't have to worry about that with trees. We just said as soon as it's null, we don't worry about it anymore. So that's the idea behind breadth first search, is looking at all the neighbors at once. Now there's a few other interesting things about this that we can discuss. One of them is starting point. You know, how do we know we start there? And the answer is we don't. But first, let's talk about the basic algorithm, and then we'll come back to this. So the idea here is we have here a breadth first search, and we pass in a graph and a starting point. And what we do here is it's basically set up, it's again just rough pseudocode, it's basically set up like level order was, where I say for all vertices in G, or I should say for all vertices V in the graph, V dot mark equals 0. The book describes it as encountered is the name of the field on the vertex. I would use that, except I'm going to run out of room on the piece of paper if I have to write encountered all the time, possibly. So I'm just going to say V dot mark, and I'm going to write 0 instead of true. And all we're going to say here is we then say on Q start vertex, which is one of those vertices we just marked as 0. And so then we say, well, now that we've done that, this is exactly the equivalent of having said we put the root element on the queue. The last thing we need to do is say our mark or our encountered for start equals 1, equals true. Because we're saying, okay, well, I've reached the start vertex. That's where I'm going to start, so that's true. And then we have that loop. And I simply say, as long as it's true that the queue is not empty, or in other words, as long as it's false that the queue is empty, what I'll do is I'll say some vertex W equals, if I run the day queue operation on the queue, and then the book's got this thing that's termed visit. And I'll mention that what that is in a moment, but for now I'll comment it out. And then we say for each neighbor X of W, and what we do here is we say, well, if the neighbor has already been marked, I don't want to re-add it to the queue, and so I can say if x.mark is equal to 0, then we'll go ahead and say x.mark is equal to 1 instead, and we'll on-queue and that's all there is to it. What we have here is, well, this is to a large degree the same fundamental algorithm we had for level order. The differences are, for level order, we said, well, pull your tree node off the queue, and then for both the left and right children, go ahead and put those children on the queue. But you only did that if the vertex you had pulled off was not null. So you had some pointer to a vertex, and you'd say, day queue my pointer, and then as long as the pointer isn't null, then you put the children on the queue. And what we're essentially saying here is something similar. We're saying for each, here it's sort of like checking the children in advance. And we're saying, we could have in level order said, we'll check the children and make sure that we don't put them on the queue if they are null. We're not worried about that here. What we're saying here is, well, if the vertex has not been marked yet, it hasn't been processed. We just are reaching it for the first time. So say, mark it that we have reached it and put it on the queue. That way later vertices can't put this vertex again on the queue again. What we're saying is, if it's been marked, then that means it's either on the queue or has been through the queue. If it's unmarked, we haven't reached it yet. So we're basically saying for all my neighbors, all the ones that haven't already been put on the queue, mark them and then put them on the queue. And that way every vertex gets one shot to go through the queue, but it can't be added to the queue a second time. And that's really the only difference here. Instead of looking at 2 of my children and saying add them to the queue, we're saying look at all of my neighbors and add them to the queue. And so that's one difference. We have potentially more than 2 neighbors. But the other difference is we're not saying add each neighbor to the queue all the time. We're saying add each neighbor to the queue only if the mark is 0. And in the process, adding it to the queue means we change the mark to 1. Otherwise, this is essentially the same idea as level order. We're just saying, well, we have this mark field that, every time it goes in the queue, the mark field is 1. The visit idea here is simply whatever you're doing to that vertex. And so in our level order traversal we wrote out, we were printing out the vertex value, and we were saying, well, you could do a number of different things. That was just what we were using as an example. And the same thing applies here. This is presumably some constant time thing. If it's not, then the running time is calculated separately, because the breadth first search here is going to be linear time for graphs, which is v plus e, and I'll talk about that in a moment. And when we say the running time for all of this is v plus e, or order v plus e, it assumes that whatever our visitation work is constant, printing out the index at some vertex, the city name if it's a bunch of cities or something like that. If this is more complicated, then the running time for all this would be v plus e times whatever the running time is for visit, because you'd be doing visit once at each vertex. And so, or I should say v times whatever that is plus the number of edges. But we're not going to worry about that. We're just saying, well, the running time for this is v plus e, and then we're assuming your visitation work, whatever it happens to be, whatever it is you're doing on each vertex, is constant, whether reading something out or setting something to 0 or printing something out or whatever. Now, the other thing you might ask is, well, when we say for all vertices, isn't that a traversal? And indeed it is. But that traversal is just based on the graph structure. So we've already seen with the graph class how we can sort of look at all the vertices one by one, going from first vertex and then the next vertex and the next vertex. And we could have done the same with any adjacency list implementation, just traverse down the collection of vertices and set them all to whatever. For an adjacency matrix implementation, we'd have the vertices stored somewhere else, and we do the same thing. Just kind of traverse across the array or the list of vertices and set all the mark fields to 0. Breadth first search is a conceptual traversal. So we could have stored, for example, when you say a heap, a complete tree, can be stored as an array. And so you say, well, because the complete tree can be stored as an array, you could just traverse the array cells from 1 to n. That turns out to be a level order traversal on the complete tree. You could also traverse the array cells from n to 1. And that wasn't any particular traversal we had discussed. But because the tree was implemented as an array, doing that was easy. Now, if you just have the tree drawn conceptually, root, children, going from the lowest level to the highest level, from level n to level 0, is a little harder conceptually to write out how that might be coded. But the fact that it's implemented with an array makes it easy. And likewise here, just saying, oh, for all vertices, go down them one by one, that's just part of the implementation. But the breadth first search is a conceptual means of writing out the particular traversals on the graph, and that's what we're concerned with. The order in which we look at the vertices here is different than the order in which we look at the vertices, just by saying however they happen to be connected, we have a set of vertices, and we go down that list of vertices like we talked about a few lectures back. That's just, okay, look over all the vertices. This is a particular ordering, a particular way in which we want to traverse. Just like we could have looked at the tree nodes in whatever order we felt like looking at them, the pre-order, however, was a particular way to do that. And so that's what's going on here. When we have this sort of for all vertices, we're just traversing down the list or array of our implementation structure. But overall here, we're after a particular order. And so this is a traversal for convenience. When we say mark everything 0, this whole thing gives us a particular breadth first search order. And that we're after specifically here the breadth first search traversal as opposed to just any old traversal we feel like. So that's the difference here. And that's what visit is then. We're just there saying, well, we have here the ability to actually reach, a particular vertex and do something with it. And whatever it is, we're assuming for the moment it's constant time. So one thing that is worth mentioning, now that we've looked at the code, one last thing. Notice here, every vertex gets on-queued and day-queued exactly once, just like with level order traversal. And so we say, well, there's some vertex processing that goes on. In addition, we're looking at the mark field of every time there's an edge from one vertex to another. We're going to explore. We're going to say, well, it's a neighbor. And we'll do this comparison and say, well, I can reach this vertex from this one. So let's check its mark field and see if it's 1 or 0. That will be done once for every edge. Because when we say for each neighbor, for every edge, we will at some point in this algorithm have its source as W and its target as X. And so total, then we do some vertex processing and some edge processing, and the total running time for this is order V plus E. Order V because that's the same as order N for level order, and now that we have to check and make sure the neighbors are marked, then that's the edge processing, and so that is the E that gets added to that. So if we go ahead and put the graph back, we can of course have different starting points. And so, actually, let me just sort of do this. This is the graph. I could of course, picked a different starting point other than A. This was the depth first spanning tree I had one of the ones I had when I started at A. I'll do it this way. And likewise, if I had started at, say, E, I could have said, well, what are the neighbors of E? Well, they are D and G and H and F and B, because there are 5 edges coming from E, so we have 5 children. Now, what can I reach from D that hasn't been reached yet? A and C. And then it'll turn out, well, now we've got all the vertices in there. So there'll be nothing from any of these vertices that hasn't been reached yet. And so there's a possibility if we have a different, whoops, just looked at the screen. If I have a different start vertex, then I can get different trees as well. Now, as far as this goes, when everything's connected, you're guaranteed to be able to do it all in one spanning tree. But what if things weren't connected? Or, if I sort of had F disassembled and these, by which I mean, if these 3 edges were not there, then F would be off by itself. And how do we do a breadth first spanning tree on that kind of a graph? Or more generally, how might we handle the situation if it was directed? And so let me draw the same graph, but let's have it directed. And the solution we use for this would be the same solution we'd use if we had an unconnected graph that was undirected. So I have here A and C, and let's say I have a connection there, and I have a connection from A to D, and here I have G, and we go to here to C and to D, and maybe that's a connection there. And there's a connection to B. Here I have E. F, H, and I say here, well, now I've got that, and that, and that. And let's say here I've got there. Now I've taken that same graph and added direction to all the edges. And then let's say I start at vertex A again. Well, again, I can go from A to, well, C, D, and B are all neighbors. So I can still go from A to C, and to D, and to B. From C, I have exactly one neighbor, which is D, and I can't go there, because that's already been added. From D, I have no neighbors whatsoever. From B, I have exactly one neighbor, which is F. And from F, I can't reach anything else. So we've got this problem here. I've looked at A, and from A I went to all the vertices I could reach, and from there I went to all the vertices they could reach. C can only reach one thing, and that's already there. D can't reach anything, because D is not the source of any edge. And B can only reach F. And then from F, we couldn't reach anything. F was not the source of any vertex. So we're stuck. We've never added H. We've never added G. We've never added E. What do we do? And the answer is we start again. We pick a new vertex, and we proceed with a second spanning tree that doesn't include any of the earlier stuff. So say from H, I can go to G, and I can go to E, and then that's it, because now I've added everything. So what I have now here is these two trees together make up the breadth first traversal, and this can be known as a breadth first spanning forest, because we have two spanning trees, so this is a spanning forest. But the idea is if I start somewhere and I eventually reach a point where I've done the full traversal and I'm now all out of vertices, but I haven't reached all the vertices yet, so I say, well, now I've looked at all these, I've looked at this, and now there are no more vertices to proceed with the algorithm, but I've got three I never looked at. But they weren't children of A, and they are neighbors of A. They weren't neighbors of any A's neighbors. They weren't neighbors of any of those. The algorithm's run its course, and yet I have three that are unmarked. We pick one of those three, and we start again. And so now that's how that would proceed. And in general, if you've had an unconnected, undirected graph, or however it happens to work out, if you finish your spanning tree and you haven't marked all the vertices, then you start at some unmarked vertex and proceed. And you can even code that by doing something like this, where we could have removed the marking from the breadth first search here. I could have, when we look at the code, I could have gotten rid of this part and said, comment this out, because that could have been done beforehand. So initially we had it as an initialization. Make sure all the marks are 0, and then make sure the start mark is we have that that's added to the queue, and the start is marked 1. But I could have commented that out and done something like this and said, well, I have here a breadth first search wrapper where I say, this is just my graph, and I say, for vertices in G, the mark is equal to 0, and then for all vertices in G, if v mark is equal to 0, then we'll call the core BFS operation on that graph with that vertex. What happens here is we initialize all the marks to 0, and then we say, now just traverse down the collection of vertices one by one, and for every vertex you encounter that is not marked, go ahead and call breadth first search on it. And of course, the first time, definitely that vertex will not be marked because we just set them all to 0. If I can reach all the vertices from this first one, if I call breadth first search on this first vertex, and from there I manage to mark everything else, then when I return from breadth first search and continue to proceed in this for loop, all the other vertices will now be marked, and I won't call breadth first search again. If, on the other hand, I have a situation like we just saw, where maybe I had things, in the list of vertices I had here was A, D, F, H, C, G, E, and B. And maybe that's my order of vertices. And so I proceeded like this, and as I looked, I marked A, and then C, D, B, and then F. So I said, well, set the mark of all these to 0. And then as I traverse down, I say, well, now I'll go through the list again, and every time a vertex mark is 0, call breadth first search on it. Well, that vertex mark is 0, so I call breadth first search on this, and I would set that to 1, and then I would have set each of C, D, and B to 1, and then I would have set F to 1, and then I would have returned from the BFS. And now I'm saying, well, now look at the second vertex. Oh, that is 1, and that is 1. Oh, but that's 0. So this was a vertex that was not marked with our last breadth first search call. We'll proceed to call breadth first search on that, and therefore H would have been the start of our second spanning tree, and then that would have marked those 1. And now we'll say, when we return from the second call, we now say we'll continue searching through the list. That's 1, that's 1, that's 1, that's 1. So I know somewhere in those 2 calls I managed to mark everything, and we're done. So that's how this could work. That would be how we would allow ourselves to restart at a different place, just traverse down the list and say, well, restart breadth first search at every vertex that is still got a mark of 0. And any vertices have a mark of 1, it's because the previous breadth first search call or calls marked it as 1. But if we reach one that's still got a mark of 0, it means for all the breadth first search calls we've done yet, we haven't managed to mark that vertex. So we start a new spanning tree at that vertex. And of course, the very first vertex, we're always going to call breadth first search on, because at that point we don't have any spanning trees yet. So by wrapping breadth first search in this kind of a quick code, you're then able to make sure you can start over when you need to, and create a second spanning tree with another limited part of the graph, and therefore create a spanning forest. And so in order to do that, of course, we would then say, well, you don't reset all the marks to 0 within breadth first search. You just say, okay, I've got a queue, go ahead and put my start vertex on the queue, mark it as 1, and proceed from there. That's how we can do that. And of course, this marker, this wrapper here this is going to be order V. And here we're going to say, well, I'm just traversing down here, so I have an order V loop times the cost of the breadth first search, and the total time of all our breadth first search calls overall is going to be V plus E. And so this will be, what happens here is we have the loop processing is order V time, and then that's going to be plus the individual, the total of all these calls, because sometimes you won't make the call, sometimes you will. And so it's the total here. We can't really do a multiplication. We'd like to say V times that. In reality, since we never know if that's going to run or not, or what the running time will be, this ends up being order V for the whole loop processing plus the total running time for all the breadth first search calls, which is V plus E. And so the whole thing then is still order V plus E. V for the wrapper part and V plus E total for the calls to breadth first search, as we've already discussed. And that's breadth first search. There's not much to say about that. Like I said, it's basically you've got, you can do a unweighted shortest path traversal off that. And so then the Dijkstra's algorithm that we looked at was basically a modification of breadth first search, where we used a priority queue rather than a regular queue. We said in this case, instead of proceeding with the last, the first vertex remaining that we added to the queue, we said out of all the vertices in the queue, proceed with the one that is the lowest distance. And we have to update the distances in the queue as we proceeded, but basically Dijkstra's was just saying this is going to be breadth first search, where we pull off the lowest distance vertex rather than whatever happened to be the first value, so it's priority queue in place of regular queue, and then we had to do some updates, so we'd be shifting positions around in that priority queue. But Dijkstra's was based heavily on breadth first search, which, as I mentioned at the start of the lecture, is why often we would teach Dijkstra's after breadth first search. But weighing the idea of teaching traversals in general before Dijkstra's over the idea of the TAs being able to go over Dijkstra's examples with you, I figured this was the better way to go. So that's why we did this afterwards. And that's all there is to say about breadth first search. The other possibility is depth first search. And with depth first search, if we go ahead and sort of redraw that graph, and I'm just going to skip right ahead to the directed graph example this time. We have here the graph I drew last time. We have A to B and A to C, and C is the target of an edge coming from G, which also points to D. C points to D. D is pointed to by E, which also points to B. B points to F. Blah, 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 blah. And so you got this graph then. And given this, now depth first search takes a different tact than breadth first search does, where breadth first search is concerned with kind of searching broadly over the graph. Depth first search, on the other hand, is concerned, whoops, I forgot one. Depth first search, on the other hand, is concerned with going as deeply as possible to begin with. And so what we have then is, let's say we start at A again. From A, I can go to C, one of my neighbors, and I say, rather than looking at all the other neighbors right away, I'll now look at the possible neighbors from C. And there's exactly one neighbor from C that we can reach. We can reach D. From D, we can't reach anything. So I return to C and say, were there any more neighbors I could look at from C? And we said, well, no, there weren't. So I returned A, and I say, were there any more neighbors I could reach from A? And I said, yes, there were. I could reach B. And what can I reach from B? Well, I can reach F. And what can I reach from F? Well, there's nothing. So I backtrack to B and see if there are any other vertices I can reach from B, and there weren't. So I backtrack to A and say, are there any other vertices I can reach from A other than the ones that are already marked? And there weren't. So we're done with this spanning tree. And therefore, using the same technique we used last time, we now say, well, let's start somewhere else. For example, let's start at, say, H. Yeah, I will start at H. I thought maybe there's a better way to go. Start at H, and I say, well, what are the vertices we can reach from H? And I say, well, I can reach E, for example. Now, are there any vertices I can reach from E? Yes, I can reach G. When we say vertices, we of course mean unmarked vertices. And I say, what can I reach from G? Well, nothing that's unmarked, so I return to E. Is there anything new I can reach from E? No. Return back to H. Is there anything new I can reach from H? No. So I return. That's the end of my second spanning tree, and now, of course, I've covered all 8 vertices, so I'm done. And this, of course, we have the same terminology, the idea of a depth first spanning tree or a depth first spanning forest if we have more than one tree. So we have that same terminology that we had for breadth first. But this is the idea behind the depth first search, is we don't look at all the neighbors at once. We say, well, pick one neighbor and go to that neighbor. And now pick one of its neighbors and follow that edge. And pick one of its neighbors and go there. And we keep doing this until we get down to a point like we had here where there are no neighbors to look at, or no more neighbors to look at, and there were never any for D. When we came back up to C, we then say, the idea is when you hit a vertex and there are no more neighbors to search, you return to the previous vertex and continue searching its list of neighbors. And there was only one neighbor from C, so that you returned again back to A. And A, there was a list of neighbors to continue. C had been one of them. B had been a second neighbor. D, in fact, had been a third neighbor, but now we've covered D elsewhere, so we don't cover it from A. So we have 3 possible neighbors to search from A. By searching neighbor C, we ended up covering D later on, and we didn't attach D to A. If I had hit D first, I would have said A to D. You can't reach anything from D, so I return back to A, and then I could go to C, and there'd be nothing unmarked to reach from C, so I'd return to A. So I could have just as well had that first tree start. I could have said, well, from A, I first go to D, and then return, and then to C, and then return, and then to B, and then to F from there. And then the same second tree. So if I'd started with D, that's how it would have gone, but since it started with C, I was able to reach D from C, and so it didn't point to it off of A. But that's the idea. We go as deeply as we can, and when we run out of neighbors to look at, we return to the previous vertex and ask if there's any more neighbors to look at there. And if there's not, we return to the vertex before that and ask if there's any neighbors there. And we keep basically doing that and searching over the neighbors of all the neighbors of that vertex and then returning. But the search over all the neighbors of a vertex involves recursively searching off the neighbors of those neighbors. So I'm saying here, recursively search the neighbors of C if it's unmarked, then look at do a depth first search on C, then do a depth first search on D if it's still unmarked and it's not now marked at that point, so we don't bother, and then do a depth first search on B if it's still unmarked. And so that's the idea there. We're going as deeply as we can into the graph, and the same thing happened here. With breadth first search, we had said, well, H has 2 children, E and G, so list them both. Here we only looked at one neighbor first. And then from that neighbor, we said, well, what's one neighbor we can reach from there? And that was G. And from G, we couldn't reach anything, and so I had to return to E. But there were no more neighbors to look at from E. If there had been, I would have continued looking at those, but I returned to H. And there were no more neighbors that were unmarked to look at from H, so I returned from H, and I was done. And so that's depth first search. Now, as far as the code goes, we can have a similar wrapper method. So I can say, well, let's do the wrapper for depth first search here, where I pass in the graph, and I can say for all vertices in G, v.mark is equal to 0, and then I can say for all vertices in G, if v.mark is equal to 0, then we will do a depth first search call on this graph with that vertex. And the question is, what's involved in the depth first search call? And the answer is, well, there's not a whole lot to worry about there. That's your wrapper, and the depth first search call itself, given the graph and a vertex. And of course, if this had been built as a member function of the graph, then you wouldn't be passing in the graph. You simply say here, well, the first thing you do is set the mark. Say when I do a depth first search on a vertex, I mark it. And then I say, for all neighbors W of V, if W mark is equal to 0, then we'll call DFS on W. That's the fundamental idea of this algorithm, and that's what we were doing here. I was saying, well, do a depth first search on A, and doing a depth first search on A involves saying, well, mark A, so that we don't ever include it again, and then say, look at all of my neighbors one by one, and run depth first search on them. So I'm running depth first search off of C, and that ends up with C and D marked. Then D would be marked, so I wouldn't have run depth first search off of that, even though it's a neighbor of A. And then B is unmarked, so I run depth first search off of that. And running depth first search off of C involves saying, well, mark that, and then do depth first search on its neighbors. Marking B involved, or doing a depth first search on B involved marking B and then doing a depth first search on each of its neighbors one by one. And so this procedure is recursive. At every vertex, we're saying, mark it, and then further search my neighbors one by one, which involves marking each of those and searching those neighbors one by one, and so on and so forth. And so that's all there is to depth first search. You have the same abilities you had as with the breadth first search, where if everything's connected and undirected, you only have one spanning tree. If you have an unconnected graph, the undirected graph that's unconnected, or if you have a directed graph, you potentially end up with a spanning forest instead of a spanning tree. There's also the idea of visiting, and so the book, if you take a look at the book, you've got right here the notion of a pre-visit, and right here the notion of a post-visit at this spot in the code and at this spot in the code. And all you're doing there is you're saying you can either, whatever your visiting is, if you're printing out your vertex or if you're doing something else to it, or whatever it is you happen to be doing some vertex, your pre-visit means you do that to your vertex before you look at its neighbors. And let's say if you're printing, for example, that means you print out a vertex before its neighbors. I would have printed out A before C, and C before D, and B before F, and A before B, C, D, or F. Post-visit means after you visit the neighbors, then you print things out. Just like post-order traversal would print out the root after it prints out the children. And so you have the option here of one or two or both, but doing some sort of work at a vertex either before or after the recursive calls to its neighbors. And so if your concern is then to have a printing of the vertices or whatever, you have the option of when you want to do things. Where with breadth first search, there wasn't really any need for pre-visit or post-visit. There weren't any recursive calls. You're just looking at everything in the order you add it to the queue, and so that's the same order that you visit things, in the order you add them to the queue. Where here you have the idea of, well, I can print things out in order of when you reach it, you print it out, and then you do the recursive calls. Or I can look at all the recursive calls and then print what I reached out last. So you have both options, first or last. With breadth first, you basically say, well, everything gets processed and printed or visited in the order I added to the queue. And anyway, those are our standard two traversal algorithms for graphs. There's not really a whole lot more to say about them. That's pretty much the extent of things. And what we will look at next time is topological sort, which is a means of ordering the vertices in a graph or printing them out in a special order that is relevant, that is useful for us. What we will see is an implementation based off of each of these algorithms. So in addition to the fact that Dijkstra's was sort of kind of a breadth first search based algorithm, in addition, the topological sort will have a very strong breadth first implementation and a very clearly depth first implementation as well. So you get a feel for how each of these traversals could be used in an application. But that will be next time. I'm not going to be able to tape that lecture, unfortunately, before Thanksgiving, but it's now Thursday at 6:17 a.m. This lecture's done. I got 3 of them out to you before break, and then I will be back in town on Sunday and at that point I'll finish up the last 3, Sunday afternoon or Sunday evening. So at least for once, you folks are a week ahead, instead of the local folks being a week ahead of you. And that said, now you'll remain a week ahead for the rest of the semester, at least, because I will have the rest of them done before the Monday's lecture is even given here. So now that I have some room to breathe, I can get these done. And that should cover things. I hope you all have a nice Thanksgiving, or had a nice Thanksgiving. I don't expect any of you actually viewing this lecture today, but I guess perhaps you are. Actually, some of you may not be in America, so you wouldn't have Thanksgiving today. I'm babbling at this point. I'm very tired. Anyway, hope you all enjoy these lectures, and I'm heading home to be with my family, and have a good weekend. Talk to you later. Bye.